The chapter is Electromagnetic Induction. Michael Faraday, as you know, was a great scientist. He conducted a series of experiments, number of experiments on magnetic field, the conductors and mechanical force. These experiments have finally led to the idea of invention of electromagnetic induction. This electromagnetic induction is a fundamental in generation of electric current, both AC current and DC current. Let us understand what are the experiments is conducted, the observation finally led to the idea of that invention. Let me recall this concept from the previous classes. This is the one, the conductor carrying current. It is of course a straight conductor, direction of the current, and there is a magnetic field, its direction as shown. If this is the electrical conductance and this is the magnetic field, this interaction produces a mechanical force. That force is also called as a magnetic force or Lorentz force. The direction of the force in accordance with left-hand Fleming's rule. What is the direction? Mechanical push which is produced on the conductor. Here it is the direction of the force. It is outward. That means these vectors are lie in one plane, perpendicular to each other. Direction is like this. And the force exerted is perpendicular to the plane. It is outward. The symbol says outward like this. So that is the case, conductor will make a move like this. There is a movement perpendicular to these two. Outward force. That mechanical force experienced with the conductor like this. That is what the force, magnitude of force is given by this equation. BIL sin theta. B stands for the intensity of the magnetic field. I stands for intensity of the electric current in the conductor, and L length of the conductor. The magnitude of force depends on this, and also theta, sin theta. Theta is the angle between the B and L, the straight line and L angle. In this case, I have taken this is theta equals 90 degree. It is B because 90 degree means perpendicular to each other. BIL, F is equal to BIL. Magnitude of force experience or mechanical push experience with the conductor is BIL. That is the depends on that. If this is the direction and this is the direction of the current, let us change direction of any one, either magnetic field or current. What will happen? Let us change the direction of the magnetic field. This direction as this side, opposite direction. And what would be the direction of the force? It is exactly opposite to this. If the reverse magnetic field is reversed like this, the force is inward force like this. The symbol says the force is inward. Now, what is the moment? The displacement of the conductor, it is displaced like this, inward like this. it is moving like this, perpendicular to this, and inward movement. Keeping the direction same, let us change the direction of the current. Yeah, also changes the direction like this. Any change in the direction, either this or this, we will change the direction of the force in the opposite direction. If this is a moment, this will be the moment like this in this case. It is accordance with the Fleming's left-hand rule. That is what a mechanical force or mechanical energy. It is conversion of electric energy into mechanical energy. That is the one already explained this. That is the mechanical energy generator using DC source and AC source. A conductor is a circular conductor, a rectangular shape. Maybe circular shape or rectangular. This is rectangular shape. So in this, we see the direction of the current like this, and like this. If we pass DC current through this, with this interaction, the force is, look at this, similar to this. The force is outward. Here, this is one. The force is inward. So if this portion is outward, this portion is inward, resulting in what is the rotation of the coil. That is rotation like this, anti-clockwise rotation. So for every rotation, half a rotation, got that? It will interchange, terminals are interchanged. So with this design, that is split commutator, with this what is that every rotation, this also what is that changes the polarity, plus because it is plus remains same. With every rotation of a rotation, as the terminal changes, plus will remain because of split commutator, resulting in the same direction of current as shown here at every moment. This will keep rotating continuously all the time because of split commutator. A conversion of energy, electric energy into mechanical energy using DC current. Suppose we have AC current like this. AC current alternate changes. That is, here always minus plus. It is changing plus and oscillating. If that is the case, we need this design. What is that? Slip rings. These slip rings, what is that? During every half a rotation, terminals are interchanged. At the same time, AC source is interchanging. Plus becomes minus, minus becomes plus. Simultaneously, what is that? Impedance. By the time it becomes plus, again what is that? Same direction. So, simultaneous interchange of terminals as well as AC source keep the current direction always same direction as shown. So, this will keep on rotating like this. So, this for a continuous rotation, we need this design for DC source. We need this design for AC source. It is a conversion of electric energy into mechanical energy. So, can we expect this? If that is the case, can we see this effect, this phenomena, in the reverse way? That is, can this effect be reversed? That was the idea of the Michael Faraday. So, this idea has led to that it can be reversed. What has done here? Electric energy has become mechanical energy. Let us apply mechanical energy on the conductor without current. Keeping this mind, see that current is induced in it. That effect is reversed. So, Michael Faraday idea was that the effect you tried, so it is possible that the effect can be reversed. For that one, he has taken what is that? What is a circular conductor, that is a closed conductor like a coil like this, not like a straight wire. On that conductor, he has conducted a series of experiments using magnets. Look at that, this experiment. This is a coil of course 1 ton. A circular coil is taken, a closed conductor coil, and the magnet, the bar magnet here, by moving back and forth, that is a linear oscillation, movement. By moving, that is a mechanical force, applied mechanical force, moving the magnet, keeping this coil stationary. This is fixed, that is keep moving back and forth, moving towards this and then moving away. So this oscillation, movement of oscillation, see that indication of current in the conductor. What is the direction of the current here? While the magnet is moving towards this, closer to this, facing north pole towards the coil, the current is induced in the coil, direction of the current like this, anti-clockwise direction. While the same magnet is moving away in the opposite direction, and he observed that current is also induced, but in the opposite direction like this. Look at that. Oscillation, back and forth. So direction like this, current is there. Direction like this, current is induced, but in the opposite direction, current is induced. This one experiment. And with the same set of experiment, he has repeated this. What is the repetition? The bar magnet facing south pole towards the coil. Facing south pole towards the coil. Same thing is done, moving back and forth. While moving this towards the coil, again the current is induced. Look at the current direction, not like this, it is clockwise direction. For this alignment, while the magnet is moving towards the coil. Suppose the magnet is moving away from the coil, the reverse effect. Current, what is that? Anti-clockwise direction. Look at this. N, moving forward, moving backward. Moving forward, moving backward. That is, the current is induced in the opposite direction. With this magnets, bar magnets, permanent magnet, he has tried this experiment. And next set of experiment, he has not used bar magnet, bar magnet. Instead of that, he has used, what is that? A coil carrying current, similar to this. Here, a coil in which current is flowing. The same coil stands still. As you know, a coil like this carrying current is flowing in this. It induces magnetic field. Any flow of current induces magnetic field around the conductor like this. The direction of the magnetic field for this direction of the current in the coil like this. In the clockwise, magnetic field direction like this, similar to this. North, south pole. It exactly behaves like bar magnet like this, north, south pole. With the coil carrying current, if you make a movement back and forth, similar to this, moving back, moving forward, moving backward. So when this coil is pushing towards the coil, you see that the current is induced, similar to this. No change. Replace this by this. This acts similar to this one. Moving closer to this, current is induced in the anti-clockwise direction. Suppose the coil is, what is that, moving backward, that is moving away from this, similar to this. It is not shown here. Then the current direction reverses like this. This experiment is done. So the same thing, what is that, if the current direction is, this is the one. Now interchange the current direction reverse the current direction in the coil like this. So with this direction of the current in the coil, it behaves as a magnet and magnetic field direction like this. Not so. Let us repeat the experiment, moving back and forth like this. Moving towards this. Signal to this. What is that? So, this is this one. Moving closer to this current direction induces. Moving away from this induces current in the opposite direction. That is not shown here. This is another set of experiment. Using magnet, using current carrying coil, and one more experiment using the same kind of coil with make and break circuit. Same coil, it stands still fixed. Here no movement of coil. These two coils are fixed position. Only thing make and break. When you make this circuit, current flows. When the current flows, magnetic field is induced. The magnetic field is induced, current is also induced. If you keep flowing the current constantly, no current is induced. The moment you make, see the current in, and again you break it immediately. When you break it, current direction is reverses. What we see the clockwise becomes anti-clockwise. Make current, break current in the opposite direction. What is the difference? Both the coils are fixed. Only thing you have to make and break the coil. Pass the current and cut off the current. Pass the current and cut off the current. You see that current is induced. Current is induced. When you make the break, when you make the circuit, current induces. When you break the circuit, again current induces in the opposite direction. Make and break induces current, AC current in the current opposite direction. There is another experiment. All these experiments, the observations, the important observations. What is happening in all these experiments, whether this or this or this and this? You see that magnetic field is very important. Magnetic lines of force interacting with the conductor. In all these experiments, it is observed that there is a change in magnetic flux. Here produces magnetic field, magnet. There is a change in magnetic flux in the area occupied by the conductor. This is the area of the conductor occupied. All these experiments have led to the same idea. In all these experiments, there is a change in the magnetic flux in the area occupied by the conductor. What is meant by magnetic flux? Let us understand the meaning of magnetic flux. Similar to electric flux. Magnetic flux means amount of magnetic field or the amount of magnetic lines passing through a given surface area. What amount of magnetic field? At how many lines of force passing through the given surface? That is called as magnetic flux. It is given by AB cos theta. That is the area of the given surface area, two-dimensional surface area. A stands for area of the surface. And B, there is magnitude of area of this that is designed. B is the strength of the magnetic field. And theta is the angle between the area vector and magnetic field. What is area vector? Area vector is a perpendicular line to the plane, surface plane. That is a normal. AB cos theta depends on this theta as well as AB. If the theta is 0, what is theta 0? Normal and magnetic field are in the same direction. It is same as the surface is lying exactly perpendicular to the magnetic field. That is the surface perpendicular to magnetic field. This becomes 0. That becomes 1. Cos 0 becomes 1. Then magnetic flux is AB. Is only AB maximum. This is called as magnetic flux. What is meant by magnetic flux? Magnetic flux is the magnitude or the amount of magnetic field, intensity of the magnetic field is passing through the area, two-dimensional surface area. What amount? Depends on the area as well as magnetic field. Here we see that the area is this. Here magnetic flux, not simply magnetic flux, it is a change in the magnetic flux. That is change of magnetic flux with this every movement like this. Every action will change the magnetic flux variation. Magnetic flux increases. Here when you move like this, magnetic flux increases. Increase change. When you move away from this, magnetic flux decreases. This magnetic flux. The change is important. Magnetic flux either increase or decrease. The variation of magnetic flux with respect to conductor induces current in it. That is what Michael Faraday's observation finally left with that idea is that is rate of change of. That is amount of EMF or voltage. With this action, voltage is induced, EMF is induced in the direction of this direction. EMF or voltage is induced in the current. It is depending on rate at which, that is d pi by dt. The pi stands for magnetic flux. D pi by dt, rate of change of magnetic flux with the time. Rate of change of magnetic flux with time. That is change in magnetic flux. It depends on the area of the conductor and the magnitude of the intensity of the magnetic field, and with the theta means rate at which we are moving, whether linear movement or rotational movement. It may be linear movement or rotational movement. So this rotation, speed with which magnet is moving, the speed with which magnetic field is moving like this. That is why it depends on all these things. So rate at which magnetic flux, rate of change of magnetic flux is called as the induced EMF or induced voltage. Its magnitude depends on the magnitude of this rate of change of pi with t. It depends on area of a bigger the coil, bigger is the value. And higher the intensity of the magnetic field, higher the value is during rotation. And higher the speed of movement or rotation, higher is this value. It depends on the area, magnetic field, and the speed of rotation, speed of movement of the magnet. Faster the speed, greater this value. And also depends on the n, number of turns. Here only one turn. Here are two turns, double the effect. Three turns, double the effect, number of n. So voltage induced in the conductor depends what is that n as well as rate of change of magnetic flux with time. So this is what observed Voltage, what is voltage? Induced. If the voltage is induced in the conductor, electric current flows in one direction. I'll tell you what is direction, of course. And look at this. This experiment, what is that? Practical experiment is conducted. We have a conduction, that is a coil in the form of conduction. This coil is there and a circuit is here. And the bar magnet is here. And it can be rotated about its vertical axis, like this rotation like this. During rotation it changes now. Every off rotation it becomes N becomes S becomes N. For one complete rotation again remains the same position like this. Complete rotation like this. Magnet is kept moving by rotation here. While moving, what is that? While rotating, what happens here? When it is stands, you see that magnetic lines of force. If you keep the magnet like this, nearby the coil, see the magnetic lines of force like this. Touch with the conductor. During rotation, what happens? This magnetic field or magnetic lines of force cutting through the conductor. Magnetic lines of force cutting through the conductor while rotating this magnet. That cutting through the conductor produces a change in magnetic flux. That is what? It depends on the speed of rotation, depends on the size of the coil, depends on the intensity of the coil, or that is what? A number of terms as like this. The amount of voltage here, it changes the mechanical energy, that is the rotation rate of change of magnetic flux is nothing but a mechanical energy, magnitude of mechanical energy applied on this magnet. It becomes electric current in the circuit. It becomes a voltage in the circuit. What is meant by voltage? Here there is no current. When the voltage is induced, what happens? Voltage means it is actually a push. That is a push which drives. Voltage means the push which drives the charges in the conductor. That is called as electric current. What the voltage induced or the voltage in the conductor, which is the one which drives what it drives the electric charges in the conductor. That is called as electric current. Voltage is a push which drives the electric current. How do you get this voltage? Push. How do you get this push in the conductor? It is because of mechanical action on the magnet or the conductor. Mechanical action. A mechanical work. It requires some work. What is that? Work is to be done. A mechanical work is to be done on this magnetic field or magnetic magnet, which converts into voltage, the push in that generates. So mechanical energy or work done change into electric current. That is a conversion of mechanical energy into voltage or electric current. That is what Michael Faraday idea is that. What is that? It is also called as the law of Michael Faraday. What is the law? Law is rate of change of magnetic flux is the EMF induced or voltage induced in the circuit. What the voltage induced is the rate of change of magnetic flux according to the Michael Faraday. That is what we see, that the electric energy is generated like this. But here by rotating the magnet, we get only AC cycle. Why AC cycle? Because of interchange, N becomes N. Get AC cycle like this. For every one rotation, complete rotation, you get one cycle like this. When the north pole is here, plus electric current voltage or EMF induced is plus here. voltage the plus maximum here. During rotation, here for half a rotation n becomes s, interchange. The voltage here negative voltage maximum here. When n becomes s, this s becomes n, here voltage. For one rotation again when you come here, again you put increases by this solve. That is for one complete rotation, we get one AC cycle. Plus and minus the wave. That is one cycle. And these cycles, what cycle? No, one rotation means, so these number of cycles are how many rotations if possible in 1 second. That is called as frequency. So in 1 second, how many times it is rotated, it gives the same number of cycles. 50 cycles you get. 50 rotations in 1 cycle, in 1 second, you get 50 cycles like this in 1 second. That is called frequency, AC frequency. So this is how electric energy is generated in this circuit by the action of magnetic field or mechanical action of the magnetic field or magnet. This is about Michael Faraday's law. There is one more law, Lenz's law in that. It says that in the equation epsilon is equal to minus d theta d eta by dt. What is minus indicates? The sign is always minus. It says that indicates the direction of the voltage induced or direction of the current induced in the circuit. If the current is induced, what would be the direction of the current in the circuit? That is called as Lenz's law. Look at that. While the magnet is moving towards this is magnetic flux. While moving toward this, magnetic flux increases in the area of the coil. This increase in magnetic flux induces current like this. That is anti-clockwise direction. That is a change. While moving thus, magnetic flux increases, that is a change in magnetic flux. That change in magnetic flux produces current like this. Once the current is produced in the conductor, you know that it produces its own magnetic field. Every current carrying conductor induces magnetic field. Now this coil produces magnetic field, induced magnetic field. If the magnetic field is produced, what would be the direction of that magnetic field? Direction is opposite to this. What the magnetic field induced by this is always opposite like this. If this is direction, the induced magnetic field in this direction, opposite. That is repel each other, magnetic field. So as a result of this, while moving, we experience always a repulsion. Moving is action and repulsion is reaction. Every reaction is opposite. That is current induced is always oppose the change in magnetic flux. That is increase becomes decrease. That is repulsion. So what the magnetic flux is induced, the current induced in this is in such a way that it will oppose the change that causes. The change that causes is increase in magnetic field. It tries to decrease that magnetic field by inducing its own magnetic field. That is the cause. That is the one is always minus means there is always a decrease in the magnetic flux. While moving that it increases and tries to decrease. Rate at which it decreases the magnetic field due to induced magnetic field. It is d pi by d. That is, Lenz always says that whenever an electric current or voltage is induced in the circuit, that current induced produces magnetic field which will oppose the change in magnetic flux which causes that. That is what Lenz explained. That is why it carries minus. Minus is that what would be the direction of the current while the magnet is moving. While moving this direction, while moving what is away from this? This direction is here. While moving away, magnetic flux decreases, but it will oppose. So why what is that? It produces in the magnetic flux in the opposite direction. That is, decrease means it will increase the magnetic field. While moving away, magnetic flux decreases but tends to increase the magnetic field. That is the rate, what is that opposite direction? That is why current is induced. The induced current is in the opposite direction, which tends to attract this. That is why while the magnet is moving away, it is getting attracted because of induced current and induced magnetic field. That effect is always opposite direction. That is Lenz's law. Minus says that Lenz's law. d pi by dt says that Faraday's law. Induced voltage, induced EMF in the current because of this rate of change of magnetic flux. This, let us extend this to other bigger coils and see how the AC electric current is generated. Thank you very much.